Self-attention is the most important mechanism in the transformer. It allows every token to look at every other token in the sentence. The sentence "the animal did not cross the street because it was tired." Self-attention figures out that the word it refers to animal, not street. Each token creates three vectors called query, key, and value. Query means what information am I looking for right now. Key means what information do I have to offer. Value means what content I will actually pass forward if selected. The attention score between two tokens is calculated as query.key. We divide by the square root of the dimension to prevent large values. Then we apply softmax to convert scores into probabilities. Then we multiply those probabilities by the value vectors and sum them up. This gives each token a new representation that includes context from all other tokens. A token no longer just represents itself, it represents itself in context. This is why transformers understand language better than any previous model. Context-aware representations are the core advantage of self-attention. Running one attention. Head gives one perspective on the sentence. Multi-head attention runs several attention heads at the same time. Each head learns to focus on a different type of relationship. One head might track subject-verb agreement across the sentence. Another head might resolve pronoun references like it or they. Another head might capture long-range dependencies between clauses. Each head has its own query key and value weight matrices. They are all initialized differently and learn different patterns. After all heads compute their outputs, we concatenate them together. Then we pass the concatenated result through a linear projection layer. This gives us a rich multi-perspective representation of each token. BERT base uses 12 attention heads and BERT large uses 16. After multi-head attention, each token passes through a feed-forward network. This is two linear layers with a ReLU activation in between. The same feed-forward network applies independently to every token position. It adds depth and transforms the representation further. Between each sublayer, we apply two important operations. The first is a residual connection, which adds the input to the output. This helps gradients flow backward without shrinking to zero. It allows the model to be stacked very deep without degrading. The second is layer normalization applied after the residual addition. Layer norm standardizes the values across the feature dimension. It stabilizes training and prevents exploding or vanishing gradients. This combination of add and norm appears after every sublayer. The encoder is a stack of identical layers, typically 6 to 24 deep. Each layer has multi-head attention followed by feed forward plus add and norm. Input tokens enter the bottom and contextual input X at the top. Each layer refines the meaning further based on surrounding context. The decoder has 3 sublayers instead of 2. The first is masked self-attention, which blocks future tokens. When generating the words "sat in the cat, sat on the mat," the model can't look at on the OR map because they come after. The second sublayer in the decoder is cross-attention. Here the query comes from the decoder and the key and value come from the encoder. This is how the decoder asks the encoder what the input sentence meant. Cross-attention is the bridge between understanding and generation. The third sublayer is the same feed-forward network as in the encoder. The decoder is also a stack of identical layers, typically 6 to 24 deep. At the end of the decoder, a linear layer and softmax gives token probabilities. The token with the highest probability is selected as the next word. Training uses teacher forcing, which means the correct previous tokens are fed in. Even if the model predicted wrong, training always provides the ground truth. This makes training stable and faster than feeding predicted tokens back in. At inference time, the model uses its own predictions auto-regressively. The loss function is cross-entropy between predicted probabilities and actual token. Backpropagation adjusts all weights in the model to minimize this loss. After training on millions of sentence pairs, the model learns to translate This same architecture with different training data powers all modern language models.